Although amber and lodestone were known to the ancients, electrodynamics developed as a quantitative subject in less than 100 years. That quote comes from J.D. Jackson's book, Classical Electrodynamics, second edition, first line of the book. That is a book from a course that I hope someday you'll take. It is the first graduate course in electrodynamics, and it leads the way to many, many interesting disciplines in physics. Today, our beginning in physics 2, electricity and magnetism, is the first step along the way. It gives me great pride to tell you that our daughter is going to be taking the J.D. Jackson course at the late J.D. Jackson's University, UC Berkeley, this fall. More precisely, she'll be taking it probably upstairs in our house because Berkeley, as is EKU, will be doing many of their courses online due to the COVID-19 pandemic. So for those of you who are viewing this, whether you're in this class or taking a similar class and maybe in a similar predicament, I hope that these online lectures, these YouTube lectures, will be useful as you negotiate your way through classical electricity and magnetism at the introductory level. We'll begin today with electric charges and electric forces, but before we do that, I want to give you a kind of a picture of where this course is going to go and where it fits into the much larger picture, and why I can, without embarrassment, say this is my absolute favorite course to teach. I've probably taught it 15 or 20 times in the past 30 years. We want to talk about a brief history of electromagnetism. We'll talk a little bit more in depth later. Cavendish did his electrostatic experiments in 1771. James Clerk Maxwell unified electricity and magnetism with the famous Maxwell equations in 1864. Maxwell's theoretical work was experimentally verified after his death, unfortunately, by Heinrich Hertz in the 1880s. In this course, we'll first study electrostatics, that is to say, non-moving electric charges. We'll then progress to moving charges and electric currents, circuits, followed by magnetism, and then its connection to electricity or electromagnetism. And we'll follow that up with electromagnetic waves. And that will give you a really good first course in electromagnetic theory. Understanding electromagnetism is fundamental towards understanding physics itself. We look at electromagnetism, where the electromagnetic interaction is one of the four fundamental forces in nature, which we'll talk about in a little bit. And so by learning about electric and magnetic concepts, we learn really important things about nature. We'll talk about electric and magnetic fields. This is your first real exposure to fields, and it won't be the last. For those who go on in physics, you will begin to understand that fields are the whole game, almost. Our purpose is even greater than that, though, in this course. We talk about Maxwell unifying electricity and magnetism. Unification is a very important theme in physics. Unification of electricity and magnetism was the first such unification. But as we endeavor to understand how nature works, one of the great, well, maybe the greatest holy grail in physics is to unify the four fundamental forces in nature. That is to say, gravitation, electromagnetism, and the two nuclear forces, called strong and weak force. Right now, experimentally, we have been able to unify the electromagnetic and the weak force. There are theories that do a pretty decent job in unifying the electromagnetic, weak, and strong force. But all four forces have not yet been unified. That is one of the great projects in physics. But along with that comes something that I like to call answering the big questions. What are the big questions? Well, first of all, you might ask, where did we come from? Or where did the universe come from? How did it all begin? Where is it all going? And how is it going to end? How big is the universe? What are the smallest building blocks in matter? So some people entertain questions like this to some degree, probably all do at some time or another, as they might think idly. But physicists and astronomers, astrophysicists, do this for a living, many of them. So if you're serious about studying the big questions, you want to learn the concepts behind all the physical phenomena, such as electricity and magnetism, and this is a wonderful place to start. In addition, we live in a very highly technological society. A great deal of the technology we use is based on fundamentals of electricity and magnetism, and we'll touch on those things as we go through the course as well. Some history. We know the ancient Greeks, for example, around 700 BC, rubbed pieces of a yellowish fossil resin called amber, and it attracted pieces of straw or feathers. We know that magnetite stone, or lodestone, was attracted to iron. That was probably first discovered in this hemisphere in what we now call Turkey. Most discoveries in electricity and magnetism were made between 1730 and 1890, at least in classical electricity and magnetism. Electromagnetism has largely been a mystery because about the only way we know that it occurs in nature is through lightning. Lightning is a pretty difficult entity to study. The way we study electricity and magnetism most of the time is by manufacturing it. In a larger sense, we know that nowadays electricity is everywhere. Almost every force you can think of, every interaction you can think of in your daily life, short of jumping up and down, is an electromagnetic interaction. Let's go to some history, a little more history in detail, and see what we can glean. Electrical interactions largely are based on interatomic and intermolecular forces that are responsible for the formation of solids, liquids, and all the interactions between them. So some history. Some documents suggest that magnetism was observed as early as 2000 BC by the Chinese. We talked about the Greeks getting involved with both electrical phenomena and magnetic phenomena. In 1600, Gilbert showed electrification effects were not confined just to amber, and that they were a general phenomena. And then in 1785, we have this wonderful law confirmed by Coulomb, called Coulomb's law. It's an inverse square law for electric forces, very much like the inverse square law for gravitation. Later than that, Hans Ørsted found that a compass needle deflected when it was near a current-carrying wire. Apparently, he had some insight that there was a relationship between magnetism and electricity. In the mid-1830s, Michael Faraday and Joseph Henry independently showed that when a wire is moved near a magnet, an electric current is produced in the wire. Another way of saying it is changing magnetic fields produce electric fields. And then finally, in the 1870s, James Clerk Maxwell used observations, other experiments, Ampere's law. In fact, he modified Ampere's law and was able to unify the two phenomena called electricity and magnetism. The idea of force is what's going to link electromagnetism to what we've studied previously, such as gravitation. And the electromagnetic force between charged particles is one of the fundamental forces in nature. Let's talk about electric charges. First of all, when we think of physics, there are really only three entities we worry about: time, space, and matter. And up until this course, the matter that we talked about was mass. But now we're going to add to that matter, we're going to talk about electric charge as a type of matter. There's only one type of mass that we know, but there are two types of electric charges. Thanks to Ben Franklin, we call them positive and negative, although there's no reason they couldn't have been called something else. Electrons, as we know, carry negative charges. Protons carry positive charges. And we also know the effect that positive, or I should say like charges, repel one another. Opposite charges attract one another. And so we can look at some fairly simple experiments that are done to illustrate electric charge. For example, if I have a negatively charged rubber rod and I have a positively charged glass rod, the two rods will attract one another. You see them suspended, the rubber rod suspended in space, and we see that the glass and rubber rods attract one another because they have opposite charges. Another example, if I take two rubber rods, both of which are negatively charged, we'll see that they will repel one another. So, like charges repel. Electric charge is always conserved in an isolated system. So you can't create charge or destroy charge. You can just move it essentially from one place to another. Example of this, I can rub a glass rod with silk. I have electrons that are transferred from the glass to the silk. So each electron is going to add a negative charge to the silk, leaving a positive charge on the rod. So we haven't created or destroyed any charges, we just moved it around. Electric charge is also quantized. That is to say, it comes in discrete little bundles. The fundamental unit of charge is the charge of the electron, 1.6 times 10 to the minus 19 coulombs, negative in the case of an electron, positive in the case of a proton. And in terms of free particles, charge must be quantized. You can't find a charge that is not an integer multiple of the fundamental charge, 1.6 times 10 to the minus 19 coulombs. Now we talk about quarks, those elements that make up protons and neutrons and other things. Quarks are 1/3 or 2/3 of an electric charge. However, we never see an isolated quark in nature. So we have that caveat. Yes, there are entities that have non-integer charge, but you will never find them by themselves in nature. We have several types of materials with electrical properties. First one we would talk about are conductors. Electrical conductors are materials in which electrons flow, or charge carriers flow freely. Metals are good examples of electrical conductors. For example, copper, aluminum, silver, platinum, those are all really great conductors. what will happen is that when I charge a conductor, all of the charge will distribute itself over the surface of the material. You'll see this when we study Gauss's law next unit. On the other hand, electrical insulators are materials through which electrons don't freely travel, materials like glass or rubber, wood, mylar. Typically, when you charge an insulator in a small region, the charge doesn't move to other regions of the material, not readily. A third type of material is what we call a semiconductor. Now, semiconductors generally, normally, an insulator. However, if we dope a semiconductor, typically the semiconductor may have a valence 4, but if we dope it with a valence 5 or a valence 3 element, we can cause this material like silicon or germanium to become a very good conductor. And of course, you know that silicon and germanium are two of the elements that are used in the semiconductor industry, used for all kinds of applications, computers and phones and all other kinds of things. We'll study a little bit about them, although we will leave most of the good study of semiconductors to a solid state or condensed matter physics class. Other methods of talking about electric charge, we can talk about charging by induction. So for example, we can charge by induction in a situation where that requires no contact when I introduce a charge. And the way we can think of it is let's suppose we start with a neutral metallic sphere. Now, if it's neutral, that means that it has the same number of positive charges as it does negative charges. So it starts out with no net charge. Next, what we do is we take a charged rubber rod and place it near the sphere. Don't touch the sphere, but what will happen is all of the positive charges in the sphere will migrate towards the negatively charged rubber rod. All of the negative charges will migrate away. Thirdly, we attach the sphere to a ground wire. And what that does is it will attract negative charges to ground. We remove the ground wire, and what remains is the fact that I've got a sphere that has many more positive charges than negative. So what I have is essentially a positive charge induced in the sphere. Finally, if I remove the negatively charged rod, the electrons in the sphere will redistribute themselves, the positive charges will redistribute themselves so as to get as far away from each other as they can. And now I have redistributed the charges in the sphere. So I have a positively charged sphere and of course a negatively charged rod. That works for a conductor. In the case of an insulator, I can do the same thing. This is how when we rub a charged balloon against our clothes and it will stick to the wall, the way it works is the charges within the insulator are moved. What will happen is in the wall, it will induce a charge separation between the negative and positive charges, even if the wall is completely neutrally charged, and that will cause the positive charges in the balloon to be attracted to the negative charges in this position at the wall. So that's an example of how you can induce charges in an insulator rather than a conductor. So these are all sort of physical entities regarding electric charge. They're a decent background, and now that will allow us to move on with a more quantitative understanding of electromagnetism. The first person we're going to talk about in our story of electromagnetism is Charles Coulomb. He was a French physicist. What he's mostly remembered for, though, is Coulomb's law, the fundamental law in electrostatics. He came about this law, if you remember the Cavendish experiment from gravitation. He did a very similar experiment that Cavendish did, but in this case, instead of using uncharged balls, he used charged balls. Found that when he did an experiment, he had 2 charged balls and two positively charged, 2 negatively charged balls, and he found that the force between those balls was proportional to the charge of each ball. It was inversely proportional to the distance squared between the large and the small ball, and was able to deduce the constant of proportionality between the force, the charge, and the charge separation. And the way we write that we'll call it F sub E for electrostatic, is the constant 1 over 4 pi epsilon naught Q1 over Q2 divided by R squared in the R hat direction. What does that mean? First of all, what we're going to do is introduce the term point charge. That is essentially a particle that has 0 size that carries an electric charge. We can very well describe many electrostatic behaviors in terms of point charges. And Coulomb's law refers to point charges. What it essentially says is the force is going to be attractive if the charges are of opposite sign. The force is going to be repulsive if the charges are of like sign. And it's a conservative force, as is the gravitational force. I'd like to compare, in fact, the 2 expressions. In gravitation, we talk about the force between 2 masses as the product of the masses times some constant, big G, which is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. It's an inverse square force, so it's proportional to 1 over the distance squared between the 2 masses. And it's along the line, this R unit vector is along the line between the 2 forces. If this is distance R, the R unit vector, remember, has a magnitude of 1 and just is along the distance of this R vector. The same thing applies for electromagnetism. Instead of with masses, we're talking about charges. Q1 and Q2 are charges in units of coulombs. R squared is measured in meters. This constant, 1 over 4 pi epsilon naught, is a constant that in some texts we'll use K sub E, which I really discourage you from using because I like to use K for other things. But in our case, this value, 1 over 4 pi epsilon naught, is equal to approximately 9 times 10 to the 9 Newton meters squared per Coulomb squared. You can see immediately how much larger the gravitational force, the electrostatic force is going to be to the gravitational force. Look at the difference in the size of these 2 constants. Epsilon naught, by the way, is what we call the permittivity of free space. For reasons that I don't remember or probably don't matter at this point. It has a value of 8.85 times 10 to the minus 12 farads per meter. A farad is a unit of capacitance. We'll get to that later in the course. So this is Coulomb's law. Now, so as you can see, just judging by the constants, the electrostatic force is much, much greater than the gravitational force. And we can illustrate that in a really beautiful example that my colleague, Dr. Mark Pitts, showed me one time. And that is the following. Take your cell phone and hold it on the top of your palm, like so. Notice what's happening. The gravitational force on the cell phone is the Earth, the entire Earth pulling that cell phone downwards. All you have to do is put the top of your hand in the way, and you have balanced off the force of the Earth. This is an electromagnetic interaction, the interaction between your cell phone and your hand. And it's strong enough to balance the pull of the entire Earth on the cell phone. So, as a way to end our first lecture, let's remember the electrostatic force is a much, much greater force than the gravitational force. We'll talk about just how great that is at the beginning of the next session. Thank you.